Okay, so what we're doing in lecture 9 is learning how to calculate bending stress. So that is the stress that arises from an internal moment. So what we're going to do is we're going to start by just looking conceptually at how a rectangular beam deforms under an applied moment. So I'm going to try and draw this actually using straight lines for a change, so we get something that's reasonably nice and neat here. Okay, so here's our beam, and I'm going to put a few markers on it to mark out different sections along the beam. So we've got sort of these segments like this that are making up the beam here. Okay, that's great, and I'll just trim off the ends here. So this is our beam with a few, this is a side view of the beam with a few vertical markers drawn on it, and this is before the beam's deformed, so in its unloaded state. And then what we're going to do is we're going to apply moments like this to either side and look at how the beam deforms. So I'm going to draw the deformed case, and then we'll look at how those lines change there. So bear with me for a second while I try and get some nice pictures here of how the beam might look when it's deformed. And this is going to be a fairly exaggerated representation here. Okay, let me just center this a little bit, and then we're not looking too bad. Okay, there we go. And let's move this. You'll see where I'm going with this in a second once I start erasing some things. So let's erase some of the excess here that we don't need. I was just drawing those circles to get a nice curve. Right, so drawing lines here, we try and draw our lines so that they're perpendicular to both the top edge and the bottom edge of this beam. And in order to do that, I sort of need to make lines that angle outwards. This isn't a very good one over here. Redraw that one there. Right, there we go. So let's trim off our excess here again. Right, we'll just tidy up those edges. Right, so there's our deformed beam under the applied moment M. Okay, I'm just going to shift this over a little bit. There we go. Okay. So the thing to realize here is that if this distance between each of these lines on the undeformed case was D, then after the beam undergoes deformation under the influence of the moment that I've drawn, then that distance there is something that is greater than the distance D. So the top of the beam has been stretched. In other words, the top of the beam is experiencing a tensile strain, right? So we've got a tensile, normal, strain, epsilon, tensile. And conversely, the bottom of the beam here, that length is shorter than the original distance D we started with. So this distance is less than D, right? And that means that there is here a compressive normal strain. compressive normal strain, epsilon comp. And then at somewhere in between the top edge and the bottom edge, there'll be some position that the length between the lines is exactly what it was before deformation, so it will be D. Right? So we've got some position in here that is D, and at that location, right, there's no length change, so there's no strain. Right, no strain at that location. Okay. Now, if we look at, let's look at the deformation over the internal cross section when we do a section cut here for this next part. So I'm going to just flip to a new page to give ourselves more sketching room here. So what I want to do now is I'm going to look at this same situation, but pretending that we were taking a section cut through this segment, okay? And then I'm going to look at that cross section in 3 dimensions. Okay, so let's say, again, let's just make this simple and say that this is a rectangular beam, and I'm going to draw this nice and large here. Okay, so there's our section cut, and the rest of the beam goes this way. And here's the centroid of the cross section, and we've got a horizontal centroidal axis, right, that's passing through the cross section, and our internal moment in this cut section would be acting around in that direction. So if I flip back to the other page here, right, we're drawing this section cut. So if I was to do the quick doodle on this page like we usually do, just to show you what we're doing, we'd have this moment here, and then our internal moment would be acting in that direction. So it's this portion of the object that I'm drawing on the next page, but in 3 dimensions. So our section cut, the internal moment, and the remainder of the beam going out to the left. So here it is there. So there's our centroidal axis and the centroid of the cross section, which is located right in the center, being a rectangular beam. And we've said that the action of this internal moment, what it's going to do is it's going to take the bottom of the beam down here and compress that in on itself. So there's going to be our compressive normal strain down there. And up at the top of the cross section, that internal moment is going to pull that material outward, and that's going to be our tensile normal strain up there. And then along the axis of M, right, along the centroidal axis, that's the location where there's not going to be any strain. So points on this axis experience 0 strain. And for this reason, that axis is called the neutral axis of bending. So it's called the neutral axis of bending because there's 0 strain along this axis. So all points in the material along that axis experience 0 strain. And the neutral axis of bending, the axis that experiences 0 strain, is always the axis that passes through the centroid of the cross section. So you can have axes that pass through the centroid in multiple different orientations. For example, we could have a vertical centroidal axis. But in this example, we've got an internal moment that's acting around the horizontal centroidal axis. So that's the one that we're concerned with. So no strain along the neutral axis of bending, which corresponds to the centroidal axis, which is the axis that the internal moment acts about. So zero strain there, tensile strain at the top. So moving downward from the top, we have a decrease in strain as we move toward the neutral axis. So moving downwards, the points along this line experience smaller and smaller levels of tensile strain until we get to the neutral axis of bending, where there's zero strain experienced. And then we start getting compressive strains that increase on the other side of that axis, moving to the bottom of the cross-section that experiences the largest compressive strain. So we just have a mirror image of the top here, where the strains flip from tensile to compressive, and they get increasingly large as we move downward to the bottom of the cross-section. And I'm just showing these strains along this edge that's closest to us here, but these strains really exist all over the face of this cross-section. So all these points on the top of the cross-section here experience tensile strain as well. And similarly at the bottom, all points experience compressive normal strain. Okay, so what have we learned from this? Well, what we can do is let's define a variable here and say that if we were to measure distances in the cross-section away from the neutral axis of bending, okay, so let's say this is our starting point, our neutral axis of bending, and we're measuring distances perpendicular to the neutral axis of bending in this direction, and we call that our variable, a distance variable y. Then what we can say is that when y is equal to 0, we know that our strain is equal to 0. And when y is equal to the maximum value of y, so that's the farthest we can go away from the neutral axis of bending within the cross-section, then our strain is going to be the maximum value of strain. And because the change from zero strain to maximum strain is linear, then we can just write a linear relationship saying that the strain at any point is going to be where we are relative to the neutral axis of bending divided by the maximum distance y multiplied by the maximum value of strain. Okay, so here if we replace y with y max, we get epsilon equals epsilon max, and if we replace y with 0, then we get epsilon equals 0. So we can then take Hooke's law and say, well, the same expression or relationship could be true for stress. So recognizing that stress sigma is just modulus of elasticity multiplied by strain for stresses below the yield stress, then that same expression is true for stress. We've got stress is distance y divided by y max multiplied by sigma max. Okay, so now that we've got that little relationship there, what we're going to do is a similar thing to what we did in the lecture with calculating shear stress from an internal torque, so the torsion lecture. We're going to develop an equation that relates the internal moment m to our normal stress, okay? And we're going to use this little relationship that we've developed when we go to do the math on deriving that equation. So let's take the same picture of the cross section here that we have on that page and use that as the basis for deriving this equation. And again, deriving these equations is nice because it can tell you a little bit about the applicability of the formula. And then also, the more of these that you see, the more confidence you have in developing equations like this yourself. And then at some point in your career, when you have a situation where you don't have an equation to use, you can think about developing one from first principles like this. So here's our internal moment here, and what we're going to do is we're going to consider some little piece of, actually maybe I'll draw that in red, some little piece of material within that cross section, and it's going to have an area of dA. And we know, being above the neutral axis of bending for a moment in that direction, it is going to be experiencing a tensile normal stress. So here's normal stress sigma, and the location of that piece of material relative to the neutral axis of bending, the centroidal axis, the axis that M is acting about, is given by distance y. Okay, so what we want to think about is we want to think about where that internal moment M comes from. Okay, so if we take the stress sigma and we multiply it by area dA, that gives us a small normal force dN that's oriented in the direction of sigma. Okay. And then if we were to take dN and we were to multiply it by y, that would give us a small moment, dm. So our moment dm is then equal to y sigma dA. Now, it's that small little moment dm, the summation of those small little moments from all the elements of material, that actually produce the internal moment m. So we've got a situation where m is just simply the summation of dm from all those little bits of material, which is the summation of y sigma dA. Okay. And then if we want to compute that, of course, we replace that with an integral sign. So we need to integrate all the way over the area sigma y dA. There we go. And that's equal to m. So we're starting to get here a relationship between the internal moment and stress due to that internal moment. Now what we need to do is we need to recognize that our stress sigma here, we know that it varies over the cross section depending on where we are with position y. So we don't want two different variables here that both depend on where we are relative to the centroidal axis and the neutral axis of bending. We don't want both sigma and y. We just want one variable. So we want to think about substituting one of those out. So this is where that expression that we had on the other page comes in. We had sigma is y divided by y max multiplied by sigma max. Right? So we can substitute in this right-hand side of the expression for sigma, and then we get something where sigma max is a constant with respect to area A, and y max is a constant as well, and then we've just got variable y there. So let's do that. So we have m equals the integral over the area of y max sigma max y dA. And then we can do a little bit of rearranging there. Like I said, sigma max and y max are both constants, so they can move outside of the integral sign. So we have m is equal to sigma max over y max, and then the integral over area of y squared dA. Now this integral here, the integral of y squared dA over the cross-sectional area, that's the mathematical definition of moment of inertia. So that is moment of inertia I. Recognizing that, we can rewrite the equation as sigma max is my max over I. Now what we want to do, we've got a useful equation now. We've got a relationship between the internal moment and the maximum stress in the cross-section, but it would be better if we had a relationship between the internal moment and the stress at any point in the cross-section we want. So we can just substitute back in using that equation that we just substituted for on the other page. So the sigma is y over y max, sigma max. Right, we just rearrange that and substitute back in for sigma max. So then we have sigma y max over y equals m y max over I, and we can get rid of those y maxes, and that leaves us with our equation sigma equals my over I. So that is our bending stress equation. Okay, so let's flip to a new page, and I'm just going to go through each of the three variables in on the right-hand side of that equation to make sure that you understand how they're used to calculate stress at different points in a cross-section. Okay, so I'm going to draw the that cross-section that we had again. There we go. And centroid is located right there. Centroidal axis and our internal moment m acting about that. Okay, and because this is the horizontal centroidal axis, let's call it axis xx. So then m would be m about x, m subscript x, the internal moment about the xx axis. All right, so let's look at our bending stress equation, sigma equals my over I, and think about how that's applied when we want to calculate stress at different points in this cross-section. So let's say we have some point 1 that we're interested in, and another point, let's make it maybe right here, point 2 that we're interested in. Okay. So if we wanted to calculate the stress from internal moment mx at point 1, so the stress at 1 from mx, then the internal moment in the equation that we want to use is m subscript x, and our distance y in this equation is always the perpendicular distance between the axis of your internal moment that you're considering, so that's the xx axis in this case, and the point of interest. So if we want the stress at 1, then this is the distance that we'd use y1. So this would be distance y1 here, then divided by, and if we're looking for the stress due to moment mx, then the moment of inertia that we take in this equation has to be the inertia of the cross-section about the axis that the internal moment is acting about. So we need the moment of inertia of the cross-section about the xx axis in this case. If we wanted to calculate the stress at location 2, then we use the same internal moment because we want the stress due to internal moment mx. The distance y, again, is the perpendicular distance between the axis of your internal moment and the point where you want to calculate the stress. So this is distance y2, and that goes in the equation here, y2. And then because mx is acting about the ix, or the xx axis, you need ixx here. Okay. So again, m is the internal moment of interest. Y is the perpendicular distance between the axis of m and the point where you want to calculate the stress. Let's write that down. Y is perpendicular distance between axis of m and location where sigma, our stress, is desired, right? And then I is the moment of inertia about the axis of m. About axis of m. All right, so let's steal this drawing for a second here. We'll paste it onto a new page. There we go. And instead of having a moment that is acting about the horizontal xx axis, let's look at how we would calculate stress at these two locations if the moment instead was acting about the vertical centroidal axis, the y axis. So in this case, I'm just going to put the moment on in that direction. So let's say we have our moment m subscript y in that direction there. So looking at our equation again, sigma equals my over I. How would we calculate the stress at location 1 that arises from internal moment my? So the stress at location 1 would be, well, we'd use the internal moment my as our moment. Our distance y here, remember, it's the perpendicular distance between the axis of the moment that you're dealing with and the location where you want the stress. So that would be our distance y in this case. So that's our distance y1 here. Okay. And then we're dividing by the moment of inertia of the cross-section about the axis that the moment's acting around. So this has to be Iyy down here. Stress at location 2, we use the moment about the y-axis, and then our distance, again, it's the perpendicular distance from the axis that the moment's acting about to the location where you want the stress, right? So this is our distance y2 here. So we've got y2 and then Iyy. Okay, so you should hopefully have a good idea now of how those different variables in that equation relate to the point where you want the stress and also the internal moment and the cross-sectional properties that you're dealing with. So in order to actually start doing problems, calculating bending stress, of course, you need to be able to calculate moment of inertia for different cross sections. So it's worth doing a bit of a review on that. So moments of inertia. Okay. So we'll go over a few sort of common cross-sectional shapes here. So we see rectangles, things with rectangular cross-section a lot. Here's our horizontal x-x axis. Here's our vertical y-y axis. And let's say our cross-section has some sort of width W and some sort of height H. The moment of inertia for a rectangle is 1/12 base times height. So if we want height cubed, so if we want the moment of inertia about the x-x axis, here we're taking 1/12. The base is W, and our height is h cubed. Okay. Here, the base, remember that the base is always parallel to the axis that you're taking. Okay. And then you cube the dimension that is perpendicular to the axis that the moment of inertia is being taken about. If we wanted the moment of inertia about the y-y axis, IYY, then our height becomes our base, and we've got 1/12 HW cubed instead. Things with a circular cross-section, we occasionally see things with a circular cross-section that are subject to bending. Think of your traffic light standards, for example. And of course, if you've got something with a circular cross-section, the moment of inertia about any axis that you take is going to be the same. So XX, let's do those in red, XX and YY are going to be the same. So we have IXX equals I, YY equals pi over 64 diameter to the 4th power. Okay. What other cross sections do we have? If we had, let's say, a box beam cross section where we've got a rectangle here, like that, but it's got a hole in the center of it, like this. So the centroid is here, and we've got our horizontal XX axis. And if we wanted to calculate IXX, all we do is calculate this as a superposition problem where we take the moment of inertia of the whole outside of the cross section and then subtract the moment of inertia of the missing material. So if we do a bit of color coding on this and say that the outside here is in blue, then we're taking the I for the outside, and then we're subtracting from that the I value for the hole in the middle. Okay, and let's put some dimensions on there. So let's just call this A here and B here, and maybe that's dimension C there, and then this is dimension D there. So the way this would play out would be for the outside we'd have 1/12 and then our base and our height cubed, and then we'd be subtracting 1/12 our base and our height cubed. So we're straight up doing in here, I is the summation of individual I values for the component shapes that make up the cross section. Now we can only apply this principle where we do a straight up addition and subtraction of moments of inertia of component shapes if the centroid of those shapes all lie on the same axis. Okay, so in this case here, for the outside of this cross section, the centroid lay right at the center, and then for the whole, the centroid also lies at that same location. And importantly, they both lie on the x-axis axis, so we can add and subtract them. If they don't both lie on that same axis, then you can't do a straight up addition and subtraction. You need to use parallel axis theorem, and I'll show you what that is in just a moment. But let's look at an I-shaped cross section. So this is a really common cross sectional profile for objects that are resisting or being subjected primarily to bending stress. Something that has an I-shaped cross section is referred to as appropriately as an I-beam. Okay, here we go. Not the most symmetrical drawing, but that will do. And of course, an I-beam is really, the reason why they're used so much for bending is because it follows the principle of putting the material where the stress is. And we know that in bending, the stress increases as we move away from the neutral axis of bending. So an I-beam has very little material through the center where there's little stress due to bending, and has the large amount of material at the top and the bottom of the cross section where bending stress is the highest. So it's put the material where the stress is. Put the stuff where the stress is. Okay, so if we wanted to calculate Ixx for this cross section, here's what we can't do. We cannot, it's always, because we know how to calculate the moment of inertia of rectangles, we can, figure out the moment of inertia of a lot of cross sections by just breaking them into rectangles and adding them, subtracting them. So what's tempting to do is consider this here and this here, which should be identical. If my drawing was great. Let's call those shape number 1 and the center piece shape number 2 here. What would be tempting to do would be to say that Ixx for the whole cross section is equal to 2 times I1 plus I2. But this is not correct. We can't do that because, again, anytime that you're going to straight up add and subtract moments of inertia, you need to have the component shapes going in have collinear centroids, or centroids that all lie along the same axis and the axis that you're trying to calculate the moment of inertia about. So in this case, the centroid of shape number 1 at the top is there. The centroid of shape number 1 at the bottom is there. Their horizontal centroidal axes, right, are like this. And shape number 2, it's got its centroid there, and its horizontal centroidal axis is already marked. So those axes are not collinear. Those centroids do not lie along the same horizontal centroidal axis, so we can't do what we had just outlined. What we can do, however, is, let's flip to a new page here, and we'll just quickly re-sketch that I-beam. We can break this up into rectangles that share that have centroids all along the same line. Let's do that. So we could, for example, instead of just taking the top pieces as shape 1, we could take the whole outside as one rectangle and calculate the moment of inertia for that. So we'd say Ixx, and this is shape number 1 here in blue. Say Ixx equals I1. And then to get an I-beam, what we could do is subtract these gap regions here. So we'll call that shape number 2 there, and another shape number 2 there. So subtract 2 times shape number 2. And we can do that because shape number 1 has a centroid that's located right in the middle, and shape 2, or each shape 2, has a centroid that is located on that same horizontal centroidal axis. Okay, so they're all located on the same centroidal axis, the axis that we're looking for. So that's good. We can do that. We can do that way. All right, let's look at a cross-section where we can't do simple superposition in order to figure out the moment of inertia. So sometimes we see T-beams or cross-sections with a T shape. So that's just an I-beam, but it's missing the bottom flange. Okay, so there's our T-beam. Now, for a T-shaped beam, the centroid is the centroid of the whole cross-section, and I'm starting to draw these in black now because I'm always breaking these up into red and blue shapes and drawing the centroids of the component shapes in red and blue, so it makes sense to draw the centroids in black, I suppose, to indicate that it's the centroid of the overall shape. So the centroid is going to lie closer to the top in this case because there's more material at the top. So if we wanted Ixx here, there's no way to split this into rectangles and have all of those component rectangles have centroids along this x-axis axis. So what we need to do is use the parallel axis theorem. So we need to use parallel axis. And that is I equals the summation of I plus AD squared. Okay, so it's really like the parallel axis theorem is really like doing superposition, but you put in this extra term that corrects for the fact that the component shapes that you're combining have centroidal axes that aren't collinear. So they have centroidal axes that are at different positions, and this part of that last term in the equation accounts for that. So the way this equation is applied here, let's break this up into component shapes. So we have one rectangle here at the top, and we'll call that shape 1. And it has a centroid there and a horizontal centroidal axis like that. And then we have a component shape here, and it's got a centroid there. So this is our shape number 2, and its horizontal centroidal axis passes through there. All right, the distance d in this parallel axis theorem is the distance between the centroid of the shape that you're considering and the overall centroid location of the entire cross-section. So here, the way we'd expand this equation, first of all, is that we'd say that I is equal to, let's take this, we'd say I1 plus A1D1 squared, and then we'd add on the same term for shape 2. So we'd say I2 plus A2D2 squared. So I1 here, I1 is just the moment of inertia of shape 1 about its horizontal centroidal axis. A1 is the area of that shape, and then our variable D1 here that we square, and it's easy to forget to square these. D1 is the distance between the centroidal axis of the whole object, or the whole cross-section, and the centroidal axis of shape 1. So this is distance D1 right there. And then in our second term, I2 is the moment of inertia of shape 2 about its horizontal centroidal axis. A2 is just its area, and D2 squared, or variable D2 here, distance D2, is again the distance between the centroidal axis of the whole cross-section and the centroidal axis of the shape that we're considering. So this would be D2 there. Now, of course, figuring out what D1 and D2 are requires that you know what the centroid location is to begin with, so where the centroid is. So the location of the centroid, we always measure this relative to some datum, and I always use the bottom of the cross-section just because I like to keep it consistent, and I've chosen the bottom of the cross-section for myself, but you can do it from the top of the cross-section or any other point, it doesn't matter. But the location of that centroid relative to your chosen reference is called y bar. And we can find what y bar is by considering the first moment of area of the whole cross-section and comparing that to its component shapes. So in other words, we can say that if we take the summation of the areas, so that would be area 1 and 2, so we've got the summation of the areas, and multiply them by y bar for the whole cross-section, then that has to be equal to the component shapes multiplied by their centroid. Okay, so this has to be equal to the summation of AY bar for the component shapes. So this gives us an equation that says y bar is equal to the summation of AY bar over the sum of A. So the way this works in this case, or the way this would expand out, I'll do this on a new line here, not to mess that one up. So here we've got, we'd have A1 y bar 1. So that's the area of shape 1 multiplied by, and this is important, multiplied by its centroid location relative to the same datum that we're using for y bar. So if we're measuring y bar from the bottom, then y bar 1 has to be measured from that same datum, and it is the distance from that datum, which is the bottom of the cross-section for me, to the centroidal axis of shape 1. And then we add on the same thing for the the second component area that we're considering, so y bar 2, and divide them by the sum of the areas, so A1 plus A2. And here y bar 2 is again from the datum to the centroid of the component shape that we're considering. So when I said the first moment of area, right? If you look at this equation, this is just really a sum of the moments equation that is pretending that every unit area is one unit of weight. So we're basically comparing the relative moments of, you know, the full cross section if I flip the T-beam on its side, right? And we're looking at balancing something like this by comparing it to something that's made up of its component shapes like this. Okay. So we're just doing kind of a sum of the moments equation on areas there. All right. So 2 important equations on this page for you. This one here, parallel axis theorem, and this one here coming out of the first moment of areas. All right. What else do we need to cover in terms of moments of inertia? I think that's all we need to cover. Okay, so let's do an example problem and see how this sort of this all works. This equation for bending stress. Okay. So our example problem, we're going to have a cantilevered beam here. Okay, and it's fixed to a wall here, and let's put on our loads. So we've got a 1 kilonewton load there, and then we're going to have a point moment right in the center. That is going to be 2 kilonewton meters. And we'll put some distances on. So this distance is going to be 1.5 meters, and this distance is going to be 1.5 meters as well. And now let's draw the beam's cross section. Beams cross section. We're going to say that this is an I-beam. And it's got a cross section that looks like this. Tidy this up a bit. Okay, and let's put some dimensions on that. So the overall height of the cross section is going to be 200 millimeters, and the overall width is 150 millimeters, and then the top and bottom flanges, those are called the flange portions of the I-beam. Those are each going to be 10 millimeters, so same for top, same for bottom, and in the center, this is called the web. This is also going to have a thickness or width of 10 millimeters. Okay, so the question that we want to ask is, what is the required yield strength of the material that the beam is made out of for a safety factor of 2? So the required yield strength, sigma y, for a safety factor of 2 is the question. Okay, so looking at our bending stress equation, we've got sigma equals my over I. What we're going to want to do is we're going to want to use this equation to calculate what the maximum stress due to bending is in the beam, and then equate this to what our allowable stress in the beam is. And our allowable stress would be the yield stress divided by the safety factor. So the equation that we're going to want to work with is sigma y divided by our safety factor on the left-hand side, and then on the right-hand side we have the bending stress equation and the terms in that equation that are going to maximize bending stress. So bending stress is going to be maximized when the internal moment is maximum. So that's going to define the longitudinal position where we're calculating the stress. So we're going to want to calculate the stress along the length of the beam where the internal moment's maximum. And then within the cross section now, we want to use the location in the cross section where stress is going to be maximum. And if I just get rid of these dimension markers on the web that I drew and move those down a little bit here, 10 millimeters. The internal moment in this case for a beam that's positioned like this, the internal moment is going to be acting about a horizontal centroidal axis, and we know that stress will increase moving up or down away from that centroidal axis. So the maximum value of y, which will give the maximum stress, is either all the way to the top of the cross section or all the way to the bottom of the cross section. They're both the same. So because an I-beam is symmetric about the horizontal centroidal axis, the maximum stress at the top of the beam will be the same as the maximum stress at the bottom of the beam. One will be tensile stress, one will be compressive stress, but the magnitudes will be equal. So we want the maximum value of y in here, and then we're going to want Ixx, I about our horizontal centroidal axis here. Okay, so we know the equation that we have to work with. Now, the obvious thing to do is figure out what the maximum internal moment is, and this comes from our shear and moment diagrams, of course, or the moment diagram, and we need to draw the shear diagram to get that. So let's set up the axes for the shear and moment diagrams, and then we'll take a step back and we'll figure out what the support reaction on this beam is, and then we'll draw those diagrams. So we'll do our shear diagram in units of kilonewtons, and again set this right up below the free body diagram of the beam, and we'll change this into a free body diagram in a moment. And our moment is in kilonewton meters, and we'll set this up just like so. There we go, that's a better horizontal line. And some construction lines for drawing the diagrams would be nice. So we've got those. And now that we've got our axes set up for a shear and moment diagram, let's take off the support here at the wall and change this into a free body diagram. So there we go, that support's gone. So we can have that being a fixed support, we can have a vertical support. So I'll call that AY, again assuming that this point here is A, and we can have a moment about A. And then we could also have a horizontal force AX, but there's no applied forces in the X direction. So some of the forces in the X direction is just going to tell us that's 0. So I'm just going to erase that so we're not too cluttered here. All right, some of the forces in the Y direction is pretty trivial here. There's only 2 forces in the Y direction, so we can see that AY has to be 1 upward. And then for the moment, we do sum of the moments about point A has to be equal to 0 there. And let's see, in the direction that I've taken, we've got MA is a positive value, and the 2 kilonewton meter point moment is also a positive value, and then in the opposite direction we have 1 multiplied by a moment arm of 3, and that has to be equal to 0. So MA comes out to be 1 kilonewton meter there. All right, so we can draw our shear and moment diagrams. So shear diagram, remember you start at 0, you end at 0. Moving from left to right, the first thing we have is our point moment. That does not affect a shear diagram at all, so we move on. So we've got a point load here, 1 kilonewton upwards, so we jump upwards by the magnitude of that point load, so we're up at +1. Then the next position we're in is in this portion of the beam, and we can see that there's no distributed load. Value of distributed load gives the slope of the shear diagram, 0 distributed load, 0 slope. So that's a horizontal line. Next we have a point moment. That point moments don't affect a shear diagram, so we don't have to worry about it. 0 distributed load again, 0 slope in the next section of the free body diagram. So we just continue right on over until we get to the point moment, or the point load at the end of the beam, which takes us back down to 0. So that's about the most basic shear diagram that you can imagine. Moment diagram, start at 0, end at 0. The first thing we have on our beam, again, take a look at the beam and see where you have point moments. So we've got 2 of them, so we know we're going to have 2 vertical jumps on the moment diagram. So we want to be careful when we get to those points. So the first thing we have is this point moment. It's in the counterclockwise direction, so according to our convention, that's a jump downwards. So we're jumping down by the value of that moment. So we're down here at -1. And then next we're looking at the shear diagram. So value of shear gives us the slope of the moment diagram. So we've got constant positive values of shear, so we need to have a line on the moment diagram that has a constant positive slope. And before I go ahead and sketch this, let's just look at where we're going to get, because the change in the moment from L equals 0 here to L equals 1.5 along this line, that change in moment will be equal to the area in the corresponding portion of the shear diagram, which is going to be 1 multiplied by 1.5 is 1.5. So we are going to end up on the positive side of the x-axis here. So this value here is 0.5. Okay, that line of mine doesn't look so linear. It looks like it's got a bend on it, so I'm just going to straighten it out a little bit. There we go. So nice linear line there. Okay, now we get to the 2 kilonewton meter point moment on our beam, and that's again in the counterclockwise direction, so that's a jump down. So we are jumping down by 2, so that takes us down to, what, -1.5. And then we're in the next section of the beam now, where the value of shear remains a positive value, constant positive value. So the slope of the moment diagram has to be a constant positive slope, and that should take us back to 0. Let's check the math on that. The area inside the shear diagram, or the corresponding portion of the shear diagram, should be the change. So that area should be 1.5, and it is 1.5 times 1. Okay, so moment diagram is taken care of. So we can see from the moment diagram that our maximum moment is -1.5 kilonewton meters. Okay. Now, in terms of orientation, it's worth thinking about the orientation of that moment while we're here. So let's look at that. That moment, the maximum moment here, occurs just infinitesimally to the right of our point moment that we've got on the beam. So if we do a section cut through the beam at that location, we can see what the direction of that maximum internal moment is on a section cut of the beam. So if we take the right-hand side of the beam there and draw its free body diagram, remember we're just marginally on the right-hand side of that point moment there. Then we've got an internal moment of minus, here's our 1 kilonewton load at the end of that beam. Here's our shear, our internal shear, that's equal to 1. It's a positive value, by the way. They're positive values of positive 1 all the way across, but a positive value of shear, remember, acts to make the section rotate clockwise, and that's what it does when we draw it, so everything's looking good there. Our maximum moment is minus 1.5. Remember that a positive internal moment is bending the beam into a smiley face, so putting the top of the beam in compression. This is a negative internal moment, so it has to be putting the top of the beam in tension and the bottom of the beam in compression. So that's an internal moment that would be acting in this direction here. So this is M max equals 1.5 kilonewton meters. And note that I'm taking the negative sign out of that since I've drawn the arrow in the correct orientation of that negative, of that maximum moment. So here, this moment is taking the bottom of the beam and pushing it in compression, and taking the top and pulling it out in tension. So we've got compression down there and tension at the top for a moment in that direction. Okay, so let's go ahead and solve the problem now. We've done all the hard work here. Now I'm just going to clip this cross section out because we'll need this, and I might as well take that equation too, so we can just continue from that. Copy, and we'll plunk those right over here. Okay, so let's put in our values. Our yield stress is what we're looking for. Our safety factor was 2. The maximum moment, 1.5 times 10 to the 3 to get it in units of Newton meters. And then our maximum value of y, again, it doesn't matter if we go to the top of the beam or the bottom of the beam. We know from what we've just discussed that at this location, the top of the beam is in tension, the bottom of the beam is in compression. But because the I-beam is symmetric with respect to the axis of bending, then the value of tensile stress and compressive stress are going to be equal to one another. Okay, so if I were to just take this beam and, like, say it's projecting back that way, then our internal moment is acting about the axis in this direction, M max. So the bottom's in compression, the top's in tension, but the level of maximum tensile stress, here's maximum tensile stress at the top, and the value of maximum compressive stress, those two values are equal because the distances y are equal in both cases. So our maximum value of y is, after that long bit of talking there, our maximum value of y is 100 millimeters, 0.1 meters divided by I, which is 1/12. And then we're going to take, for I here, what we'll do is we'll take the whole outside again and we'll subtract off these two pieces. But rather than subtract them off as two individual pieces and multiply them by 2, it's even easier just to consider those two pieces as one combined piece and just subtract off that area there rather than calculate two individual areas and subtract them. So that's what we'll do. So for the whole outside, we've got 1/12 base height cubed. The base is 0.15 meters, height is 0.2, and cube that, and then we're subtracting the moment of inertia now of this center hole right here. So the base of that is going to be equal to our total base length multiplied by the thickness of the flange. So here we've got 140 millimeters, and then a height again is total height subtract 2 times the flange thickness. So we've got 180 and cube that. Okay. Safety factor. We shouldn't have written that in the safety factor because we know that we're dealing with a safety factor of 2. That was our target. So then we can solve for sigma y out of this, and we get a value of 93.9 MPa. Okay, so there we go. So now you know all about how to calculate stress due to an internal moment. In the next lecture, we're going to look at a couple of smaller topics relating to bending, how to deal with moments that are not along one of the primary centroidal axes, and also look at how to deal with calculating bending stress in composite beams. So I'll see you for that in lecture 10.